So today we have Jack Carlisle speaking on equivariant, cobordism, and generalized complex orientations.
All right. Thank you very much. First of all, I appreciate having been invited to give this talk. I'm really looking forward to the opportunity to share some of my research work with you guys or with everybody and hear what y'all think about it. If it brings to mind any research questions in your own work, etc. I want to emphasize that I want this to be as interactive as possible. So if you have questions that come up as I'm speaking or you want something to be clarified, please do let me know and I'll do my best to answer. All right, so let's go ahead and jump right into it. So a very loose sketch of what we'll do today is we'll start by going over some relevant background information. In particular, I want to define sort of the basic notions from stable homotopy theory and from equivariant stable homotopy theory that we'll need. After that, in section 2, I guess as it's labeled, we'll talk about equivariant cobordism. And in particular, I want to go through, or at least mostly go through, a calculation of the C2 equivariant cobordism ring. So this is a ring whose elements are C2 manifolds equipped with some sort of stable complex structure. Finally, in section 3, I want to talk about how this geometric cobordism relates to the theory of complex orientations in the equivariant setting. And in particular, I want to introduce a new notion of geometric orientations and show you guys some examples of geometrically oriented C2 spectra. All right, so let's get started with some background information. So I would say I identify, or at least one of the things I identify as is a stable homotopy theorist. And as a stable homotopy theorist, I'm interested in generalized cohomology theories. And so a generalized cohomology theory is just some functor which assigns to every topological space X some graded abelian group E upper star of X. And of course, we don't allow any old functor. We have to have these certain axioms that say that this cohomology theory sort of behaves like ordinary singular cohomology does. So we want homotopy invariance, we want long exact sequences, we want excision and additivity. And if you're an expert in this field, you'll know that there are some bits of missing information on this page, but this is the general idea of a generalized cohomology theory. I mean, to be more precise, we really want to assign to every pair of spaces a graded abelian group, and maybe we want to restrict to CW complexes or something like this. But in any case, these are the basic objects of study in stable homotopy theory, and I want to remind you guys of some examples of those. So first of all, maybe the first example that we ever encounter is singular cohomology. If we want these things to be called generalized cohomology theories, then ordinary cohomology better be an example of one of them. And so here we can take as our coefficient abelian group, any abelian group, and we just assign to our topological space X the singular cohomology of X. The important thing about sort of modern stable homotopy theory is that these generalized cohomology theories are essentially in one-to-one correspondence with homotopical objects called spectra. And so in the case of singular cohomology, the associated spectrum is denoted HA, and it's called the Eilenberg-MacLane spectrum. And this is characterized by a certain universal property, which I won't necessarily say, but perhaps you're thinking of if you're familiar with this stuff. Another really important example of a generalized cohomology theory is topological K-theory, of which there are many variations. So for instance, if we use real vector bundles, we end up with a cohomology theory whose representing spectrum is called KO. If we use complex vector bundles to construct our topological K-theory, then this cohomology theory is represented by a spectrum which we denote KU. And so maybe let me write out what I've sort of alluded to here, which is that K0 of a sufficiently nice space X is just going to be the group completion of a certain commutative monoid, namely the commutative monoid of isomorphism classes of vector bundles over X under the direct sum operation. Or what I've said is precise, what I've written isn't, but I hope you can sort of split the difference. Finally, perhaps my favorite example of a generalized now homology theory, so this is just the covariant version, is cobordism of manifolds. And so I want to take a second to remind you of how this homology theory is defined. The idea here is we assign to our topological space X the abelian group omega n of X. And this is defined to be just the collection of n-dimensional manifolds M equipped with a map to X modulo the cobordism equivalence relation. Where I'll do my best here in the corner to sort of draw what this equivalence relation means. The idea is that if we have one manifold M equipped with a map F down to X, and if we have a second manifold M prime equipped with a different map F prime down to X, then we identify these two objects in the cobordism group if we can find some n+1 dimensional manifold W whose boundary, and together with an extension of these maps. So a manifold W over X, such that if we restrict F to the boundary of W, we just get the disjoint union of our two maps. Now, again, what I've described here is unoriented cobordism. If we were to use a different sort of structure on our manifolds, we would obtain, or we could obtain, oriented cobordism, or maybe most importantly, complex cobordism. All right, are there any questions about these examples so far? Okay. Now, the next sort of important topic that we need from stable homotopy theory is the notion of a complex orientation. And so on this page, I want to emphasize that there are a few of these spectra which are complex oriented, namely HA, KU, and MU. And so I want to emphasize that complex oriented spectra play a privileged role in stable homotopy theory. And I'll describe why on the next slide. So before I go on and on about how important complex orientations are, I ought to tell you what a complex orientation actually is. So if E is a commutative ring spectrum, then a complex orientation of E is just going to be a cohomology class in the E cohomology of CP infinity, satisfying this restriction condition. Now, if you're familiar with these complex orientations, you might have good intuition for why we want something like this. I don't want to delve too much into why we want this particular restriction condition, but let me just tell you what a complex orientation of E gives us. So the first reason why we care is that complex oriented cohomology theories are very computable. So for instance, one thing that's nice about complex oriented spectra, and essentially, in fact, characterizes complex oriented spectra, is that if we have a complex vector bundle over a topological space X, then if we look at the cohomology of the Tom space of X, so this is sort of like a twisted suspension of the space X, this is actually isomorphic to just a shifted copy of the cohomology of the base space X. And so this is a very powerful calculational tool. Now, perhaps more significantly, we care about complex oriented spectra because complex orientations are sort of a pathway to get from stable homotopy theory to other areas of mathematics, such as algebraic geometry and number theory. So perhaps it's not worth writing, but I've already committed to it. So we start in stable homotopy theory. If we have a complex oriented spectrum, we can obtain, for instance, a formal group law, which is an algebrogeometric object, which retains a lot of the information of that spectrum E with which we started. And moreover, oftentimes, one can go in the other direction. For instance, one can start with a formal group law over some ring and then ask the question, is there some complex oriented spectrum whose associated formal group law is this formal group law which I found in number theory or which I found in algebraic geometry, et cetera, et cetera. Okay. So it's for this reason that we care about complex orientations. Now, among all,
can I ask a quick question?
Yeah, please do.
On that last slide, if you take E to be, say, just like HZ or something, do you recover sort of something familiar or for this complex orientation?
Yeah, so HZ is in fact complex oriented. So HZ is complex oriented. And maybe one thing to say about it is that associated to any complex-oriented spectrum is a formal group law. It turns out that if we start with the spectrum HZ, we end up with the so-called additive formal group law, which is essentially the simplest formal group law there is. Does that answer your question?
Yes. Yeah. Thank you.
Great. Thank you. Yeah, keep the questions coming. I enjoy that part very much. All right. So what I'd like to say now is that complex cobordism is sort of the most special complex-oriented cohomology theory there is. And that's because of the following pair of universality theorems. So first, let me emphasize part one of this theorem, which is that there is a one-to-one correspondence between complex orientations of some fixed commutative ring spectrum E and ring spectrum maps from Mu to E. In other words, the spectrum Mu classifies complex orientations. And so if we want to understand the theory of complex orientations, in some sense, it suffices to understand the complex cobordism spectrum Mu. Now, this is the homotopical universal property of the spectrum Mu. I'd like to also mention the algebraic universal property of Mu. And so this second theorem was proved by Quillen and is named Quillen's theorem. And Quillen's theorem says that not only does the spectrum Mu classify complex orientations, but in fact, if we take homotopy groups, then the coefficient ring of Mu classifies formal group laws. So Mu satisfies a homotopical universal property. If we take homotopy groups, then the homotopy of Mu satisfies an algebraic universal property. Namely, it classifies formal group laws. And so this is sort of the end of our tour of stable homotopy theory and complex orientation theory. Now, if tours were for sale, they probably wouldn't last for 7 minutes or however long this has been. So if you're feeling a little lost, that's all right. You know, we don't have time to cover all of these preliminaries, but I hope you've gotten at least a taste of what sort of topics people are interested in as they relate to complex orientations, formal group laws, etc. So for the rest of the talk, what I want to do is move into the setting of G-equivariant stable homotopy theory. And let's try to, insofar as we can, we'll sort of replicate the story of complex orientations and cobordism and formal group laws. And what we'll see is that there is much of the story which does in fact generalize to the equivariant setting, and there are some crucial points which do not. And this will be the subject of our study for the rest of this talk. Okay. So if we want to do all of this in the G-equivariant setting, we sort of need to start by defining what is a G-equivariant generalized cohomology theory. And so as one does when one tries to import concepts from ordinary mathematics to equivariant mathematics, one option is just to put G and then an apostrophe or a little hyphen before all of your nouns, and then just write it down and just see if it's true or not. Even do it in the proofs if you want. Oftentimes it doesn't work. If it worked, you know, maybe this wouldn't be worth a talk. But in any case, we can sort of do the same thing. What we want to do is we don't want to assign abelian groups not to just to topological spaces, but to G spaces. And we want this assignment to sort of take into account the G action on our topological space. So it turns out that the correct definition is that we want to assign to every G space X an ROG graded abelian group, which I'll denote E upper 5-pointed star lower capital G of X. And this 5-pointed star, as opposed to the asterisk, is denoting the fact that, or is sort of signifying that we are ROG graded rather than just Z graded. So here, ROG is the real representation ring of G. So this is our definition of a G-equivariant generalized cohomology theory. It assigns to any G space a group. This time it's G, but that's all right. I mean, this is just the appropriate G-equivariant analog of our sort of indexing set. And we want these to satisfy the G-equivariant Eilenberg-Steenrod axioms, which I haven't copied here, but they mimic the non-equivariant ones. Before we move on, let me just emphasize that for most of this talk, we'll be concerned with the group G equals C2, in which case the real representation ring of G, at least additively, is the free abelian group on generators 1 and alpha, where I'm thinking of alpha as the real sign rep of C2. And so in this special case, this is telling us that our homotopy groups and cohomology groups and homology groups are bigraded. So we'll have cohomology groups, for instance, that look like E upper M plus N alpha of X, where X is some C2 space. All right. Any questions so far?
Is there any reason why you're taking the real representations instead of the complex ones? Since we're
yeah, I mean, sometimes what is there to say? Sometimes one wants to work with the complex representation ring. And in fact, whenever one is working with things like equivariant complex cobordism, if you restrict to RU of G rather than RO of G grading, the structure oftentimes appears more naturally. But we're sort of bound to the world of ROG graded things. I mean, take this with a grain of salt. All right, I'm a student of the subject, not an expert. But in any case, I think it's sort of bound to the fact that when you take cofiber sequences, say you have a map from X to Y, they're G spaces, you can take its cofiber, that's some other G space Z. And if you iterate, if you take another cofiber, you get the suspension of that first space you started with. And that's a suspension by a real representation. That's a suspension by the real one-dimensional representation of your group G. And so for this reason, it's sort of unavoidable to work with real representations.
Thank you.
Great, thanks. Yeah, if anyone would like to chime in about this sort of philosophical rant, please do so. All right. So in any case, let's move on. So we've defined G equivariant cohomology theories, and just as in the non-equivariant case, these are represented by G spectra. And so let me give you some examples of G equivariant cohomology theories together with their representing G spectra. So perhaps the most naive thing that one can do is to define Borel cohomology. I mean, that's probably a little, I shouldn't say it like that. Borel is probably a very, very smart person, and it probably took a lot of effort to come up with this definition, but this definition is at least very natural. The idea here is this: we start with a G space X, and we sort of want to assign to it the singular cohomology of the quotient space X mod G with coefficients in whichever abelian group A we want. The problem is that taking quotients by a G action is not a sufficiently homotopy invariant operation. And so what we need to do is, instead of taking the actual orbits of our space X, we have to take the so-called homotopy orbits. And so what we do is we take our space EG, which if you haven't seen before, is just characterized by the fact that it is non-equivariantly a contractible space, and G acts freely on the space EG. We take the product with that, or we take the balance product of this space EG with X, and this is our sort of homotopical analog of the orbit space of X. So it turns out that this defines an equivariant cohomology theory, and the representing spectrum is written here. It turns out that this is the so-called co-free spectrum on the non-equivariant Eilenberg-MacLane spectrum HA. So this is sort of an analog, at least, of ordinary singular cohomology, but in the G equivariant set. We can play a similar game and or create a G equivariant analog of K theory, of topological K theory. And the idea is that, again, we can sort of construct this. I mean, it's not exactly a construction, but there is a G equivariant cohomology theory called K, or KO, or KU, and it satisfies this interesting property that if we look at, for instance, KUG upper 0 of X, that this is the group completion of the commutative monoid of G equivariant complex vector bundles over X under the direct sum operation. So this sort of formally works just as it did in the non-equivariant setting. Now, just as there were different flavors of non-equivariant K-theory, there are different flavors of equivariant K-theory. Again, here we have real equivariant K-theory. We have complex equivariant K-theory. If you want, you can construct oriented equivariant K-theory, et cetera, et cetera. All right. Okay. Yeah, and it appears that there is a comment in the chat. Let me briefly read this. So it says, the universal way to grade a cohomology theory is with the Picard group of a stable homotopy theory. Yeah, this is right. All real representations V define spheres SV, and these are invertible in G spectra, so you can grade by them. Now, I won't say the more grading you have, the better it is, but you would lose a lot of information by not doing that. Okay, yeah, thank you very much, Maxine. Yeah, this is a really insightful comment. Yeah, so the idea is that these representation spheres SV are invertible objects in the G equivariant stable homotopy category, but it's not the case that those account for all of the invertible objects, by which I mean invertible with respect to the smash product. So yeah, this is a great question, or this is a great point, and I think that there has been work in calculating the Picard group of various G equivariant stable homotopy categories. I'll probably stop talking about this before I say something wrong, but something like this is true. Okay, great. So now I want to get on to the sort of, there we go, to the main topic of our talk today, which is equivariant cobordism. So let me explain what's going on here. So on the bottom left-hand side of the screen, we have this Z-graded equivariant homology theory. We can assign to any G space X, again, the set of all n-dimensional manifolds equipped with a G action mapping to X modulo cobordism. And so we can construct this. This defines a Z-graded homology theory, but it doesn't in fact define an ROG-graded homology theory. And in fact, maybe this brings me to a better answer to the question that was asked recently, why do we need ROG grading? Well, part of it is that whenever we include ROG gradings in our G equivariant cohomology theories, we have a Brown representability theorem, which tells us that given some ROG graded equivariant cohomology theory, one is guaranteed the existence of some G spectrum, which represents that cohomology theory. And so the point here is that using the geometry, or just the topology of G manifolds, we can construct a Z-graded homology theory, not an ROG-graded one, but in any case, we can construct the Z-graded one. And we can also construct equivariant analogs of these so-called Thom spectra. These are the spectra which we expect to represent cobordism of manifolds. These spectra do represent cobordism of manifolds in the non-equivariant case. But the problem is that these two things actually don't match up. It is not the case that MOG is the spectrum which represents cobordism of G manifolds. And it is not the case that MUG is the spectrum which represents cobordism of stably almost complex G manifolds. And so it turns out that in general, or at least in the complex case, which is the thing we care about the most right now, it's not known in general whether there even is some G spectrum whose Z-graded homotopy groups are the cobordism ring of G manifolds.
Is that we don't know and most examples have it, or examples we know have it, or is it some examples don't have it, some examples have it, and we don't know in general?
Yeah, that's a great question. What I would say is this. In the unoriented case, it is known in general that there is in fact a spectrum that represents cobordism of manifolds. We know exactly what it is. In the complex case, there is a natural candidate for the spectrum which should represent this cobordism of manifolds. However, I at least do not have a proof that this really does represent cobordism of manifolds for general G. Soon I'll show you a proof that in the case G equals C2, we can sort of guarantee the representability of this candidate spectrum.
Okay, thank you.
Great, thank you. Yeah, great question. Okay, so this is the situation we're in, and this might lead you to believe that these Thom spectra, MOG, MUG, et cetera, are the wrong thing. We thought they were going to represent cobordism manifolds, and they don't, so we should try something else. But in fact, this spectrum MUG really is the right thing in some sense, and that's made clear by the following pair of theorems, the first one of which was proved in 2005, so you can see that this is more modern work. And it says that it turns out that complex orientations of a G spectrum EG are in natural bijection with ring spectrum maps from MUG to EG. So this is saying that that Thom spectrum MUG really does satisfy the desired homotopical universal property. Now, even more recently, work of Marcus Hausmann in 2019 proves that there is a one-to-one correspondence between ring homomorphisms from the coefficient ring of this Thom spectrum MUG to a commutative ring A and so-called G-equivariant formal group laws over A. And so the right-hand side in each of these blocks is sort of the G-equivariant analog of complex orientation theory. We have a notion of complex-oriented G spectra. We have a notion of G-equivariant formal group laws. And this pair of theorems tells us that the spectrum MUG is universal with respect to both structures. Okay. So where is he going? Let's find out. We've had some questions naturally arise and how I want to structure the rest of the talk. So this first part was more or less exploratory. We were just figuring out what are the definitions, what's known, what's not known. I want to sort of hone in on a couple of naturally occurring questions. The first one of which is there some G spectrum, call it omega G, representing the complex cobordism of G manifolds? So this is precisely the question we were just discussing. Now, if there really is a G spectrum representing this complex cobordism of G manifolds, can we calculate its coefficient ring? Or can we even calculate its ROG graded coefficient ring? This is a natural question to ask. If we have some G equivariant cohomology theory, well, if we can't even understand the cohomology of a point, we don't really understand that cohomology theory very well at all. Finally, if we can really find some spectrum omega G, which represents cobordism of G manifolds, it would behoove us to understand what is the relationship between omega G and the stable cobordism spectrum MUG. And so the plan for the rest of the talk is to go through and try to answer these questions in the case that G is the cyclic group of order 2. And so most of what I've said so far has just been sort of general overview of this field. From here on out is where we're going to start discussing my research that I've been doing over the last now it's been a couple of years, I suppose. So in any case, let's get started trying to answer these questions. Again, if you have any questions of your own, please interrupt. I'd love to discuss them with you. So the first question is there some C2 spectrum which represents complex bordism of C2 manifolds? And the answer is an emphatic yes. We can give a formula for it exactly. And the idea is that this is some sort of Thom spectrum. I don't want to go into too much detail, but the key point is that it is constructed using a so-called trivial C2 universe. So the idea is that any C2 spectrum associates to any complex C2 representation V some based C2 space. And we're defining the spectrum omega C2 to assign to the C2 representation V the Thom complex of the tautological vector bundle over this equivariant Grassmannian. So it's a little convoluted, but the point is just that it's some spectrum which is constructed using a trivial C2 universe, whereas if instead of writing C infinity here, I had written a complete C2 universe, that would yield the definition of the stable cobordism spectrum MUC2. So there's something in the fact that we are only allowing trivial representations of our C2 universe that is yielding the spectrum which really does represent cobordism of C2 manifolds.
Can I ask a question here?
Yeah, please go ahead.
You said you didn't want to talk about it, but what is a Thom complex?
Yeah, the Thom complex is this. So the idea if we have some vector bundle psi over x, then the Thom complex of this vector bundle is constructed as follows. What we do is we take, and in fact, let me say it out loud and then perhaps I'll have thought of a good way to write it by that point. What we do is we take our vector bundle and for each fiber, we take its 1 point compactification. So we add a new point for each fiber And then we take all of those new points we added and we collapse them down to a single base point. And so it turns out that if the base space of our vector bundle is compact, this coincides with the 1-point compactification of the total space of the vector bundle. But more generally, it's given by the description I just gave. 1-point compactification of each fiber, and then identify all those new points. All right, so here I'll write something terrible, verbal description, but in any case, yeah, thank you very much for this question. It's an important point. Okay, so don't take my word for it. I'm claiming that this represents C2 manifolds. Let me at least give you some idea for how we can prove this. And we'll see here where we're using the fact that we have a small group, namely the cyclic group of order 2. And the same proof I'll advertise also works for the cyclic group of order P. We're relying basically on the fact that the cyclic group of order 2 and that of order P has only 2 subgroups. And it makes the mathematics of CP equivariant homotopy theory much simpler. But do not confuse simpler with simple. That is a mistake I've made many times. So in any case, the idea is this. In the bottom row of this diagram, we have the so-called isotropy separation sequence. So associated to any C2 spectrum, like the spectrum omega C2 we just defined, we have an isotropy separation sequence. And it's obtained just by smashing our spectrum omega C2 with the following cofiber sequence. We have our space EC2 plus, which is defined by the universal property I mentioned before. We can always collapse that down to S0, and then we just call its cofiber EC2 tilde. So in any case, this is a canonical long exact sequence that we can associate to any spectrum. In particular, we can associate it to the C2 spectrum omega C2. And then the really interesting part is that we can also define a long exact sequence in these cobordism groups of manifolds geometrically. So this is a geometrically defined long exact sequence. So let me tell you what the terms are. So this guy we already know. This is the ring. This is the cobordism ring of, well, here I should probably stop hiding the ball. Here we're doing complex cobordism. So this means that all of our C2 manifolds actually have a complex structure, not on their tangent bundle, but on their stable tangent bundle. But this is not so central to sort of the broad strokes understanding of this topic. But in any case, it is true that we have a stably almost complex structure. And it is this ring omega C2 star whose elements are cobordism classes of C2 manifolds equipped with the stable structure. Here, omega C2 free is what you'd hope it is. This is just the ring of free C2 manifolds modulo cobordism. And finally, here we have the so-called fixed point bordism ring. Elements of this ring are pairs F, nu, where here F is a manifold and nu is a vector bundle on our manifold. And we can define cobordism of pairs like this in a very natural way. Maybe I won't dwell on that, so we have time to make it through everything we need to cover. But the point is that this map that goes from the cobordism ring of C2 manifolds to this fixed point cobordism ring takes a C2 manifold M and it maps it to the class of the fixed point locus, together with the normal bundle of the fixed point locus. So the idea here is that if we take our C2 manifold M, then when we map it over to the fixed point bordism ring, we're retaining the data of the fixed point submanifold together with sort of how it sits inside of the actual C2 manifold. That data is encapsulated in the normal bundle. And so what's the point of all this? Well, we have a morphism of long exact sequences, and so we can use our favorite or the speaker's favorite lemma, which is the 5 lemma. And it turns out that we can sort of use non-equivariant methods to calculate that both this and this are isomorphisms. And then the 5 lemma allows us to deduce that this middle map is an isomorphism. And so, of course, there's much more that goes into this than what I've just said. But the point is that the outer terms in this diagram are much more tractable and calculable than this middle term in which we're particularly interested. All right. So let's continue on. So we found a C2 spectrum, which represents cobordism of C2 manifolds. And now we're interested in calculating this ring, the ring of C2 manifolds, or more generally, maybe the ROG graded coefficients. Here, this should be a C2 of the spectrum omega C2. And so can we calculate it? Well, if we can read the faded word, then we know the answer is yes, we can in fact calculate this. Can we do it easily? Well, no, not so much, but we can in fact do it. And let me give you some sort of idea of how this is done. So here's the sort of plan of attack for calculating this cobordism. So the idea is this: we have this isotropy separation sequence, which goes from EC2 plus to S naught to EC2 tilde. And on the other hand, we have a couple of maps of C2 spectra. We have our C2 spectrum omega. By including the trivial universe, which we use to construct omega, into the complete universe, we obtain a map of commutative ring spectra from omega C2 to mu C2. Now, finally, anytime we have a C2 spectrum, we can always map to the co-free spectrum, to the Borel cohomology. So this is sometimes called the Borel completion. And the idea is we can always map this to f of EC2 plus mu C2. And so if I combine the data of this pair of ring spectrum maps written vertically on the left-hand side and this co-fiber sequence of C2 spaces that's written along the top center of the slide, I obtain this diagram of rings where each of these rows is a long exact sequence. And it is from this diagram that we'll be able to sort of obtain enough information to calculate an explicit presentation of this cobordism ring of stably almost complex C2 manifolds. The reason why we're able to do that is the following. You'll notice that in this left-hand column that's actually written in tech and not just in my own handwriting, I've just put dots instead of the actual values there. And the point is that each of these spectra, omega C2 and mu C2 and the co-free spectrum, they're all non-equivariantly equivalent. And these maps between them are non-equivariant equivalences. And so it turns out that this guarantees that these maps are isomorphisms. And for this reason, this gives us a lot, we can use homological algebra and some diagram chasing to really control this diagram very well. And in particular, what it does is this fact that these are isomorphisms, together with a little bit of homological algebra, tells us that both this square and this square are pullbacks of rings. And this is the key point, because once we have this, it tells us that if we want to calculate this omega C2 star ring, in which we're very interested, it suffices to calculate this stuff. And it turns out that each of these terms, which we can sort of go through, is much more calculable than the actual cobordism ring of C2 manifolds. So in order to get through all the material, I think I'm going to skip through some of the technical details here. The point is that the sort of salmon colored outline, if that's what color a salmon is, I can't say I've seen a salmon before, that salmon colored outline can be calculated very explicitly. That's what's written here. So instead of these mystery rings, which are the geometric fixed points and the homotopy fixed points and the Tate fixed points, if you know what those mean, we can actually write them out algebraically. And so we can see that on this bottom row, we have these power series rings modulo some power series. And on this vertical right-hand side, we have polynomial rings, or rather Laurent polynomial rings. And so I'm going to have to skip a lot of steps because this is a very complicated ring and it's a complicated calculation. But the point is that we can use this diagram right here to write down an explicit presentation of the geometric cobordism ring of C2 manifolds.
Excuse me.
Yeah, what's going on?
Was F the universal formal group law?
Yeah, excellent. That's exactly right. So here F is the universal formal group law over mu star, which happens to be the Lazard ring. Yeah, thank you. So I can see that there are some experts in this area in the audience who are picking up on some of the stuff that I'm skipping over. In any case, yeah, so this is exactly right. And in our presentation here that we're about to give is in fact given in terms of formal group law theoretic data. Let me be more precise. So this presentation, I mean, these relations look a little bit complicated, but the idea is that we just have two families of generators. We have some DIJs and we have some QJs. And this is just as an algebra over the non-equivariant cobordism ring, which we understand very well. It happens to be polynomial. But our presentation ends up referring to some other elements in the non-equivariant cobordism ring, which are defined, as I mentioned, in terms of formal group law theoretic data. So here are our generators, here are our relations, where I guess the indices go like this. And what are these elements that appear that aren't the generators Dij and Qj? Well, the Cij is defined as follows. It's the coefficient of x to the I times y to the j in 1 over the universal formal group law. Now, in similar style, this element Pj is the coefficient of x to the j in f of x comma x. So I'll let you sort of pick through precisely what this means, but the idea is that these relations are encapsulating relations in terms of formal group law data.
Sorry, is f of xy supposed to be invertible in the ring of power series? Because it starts with x plus y, right?
Thank you. Yeah. So I couldn't have planted better questions myself in the audience. Yeah. So this is not. It is in fact not a unit in the power series ring. But if you invert one of the variables, so here I'm inverting the variable y. So I'm considering this as an element in mu star Laurent series in y, power series in x. And in this ring, f of xy is in fact invertible. And the double power series ring injects into this guy. And so this is a well-defined element of mu star.
Okay. And so so here technically you could have I don't know, j to be negative, but you just choose to have non-negative j, right?
Yeah, that's exactly right. Here, there are Cij's where j is a negative number, but it turns out that these relations in this equivariant cobordism ring can only see stuff that is in non-negative degree. And maybe I won't say anything too precise. Well, I won't say this thing too precisely, but it's related to the fact that we're pulling back along this inclusion, where on the left-hand side, we have a power series ring, and on the right-hand side, we have this Laurent series ring.
Thank you.
Okay, great. Yeah, okay, great. So this is my theorem. I'm happy about this. We calculated the C2 equivariant cobordism ring, and the presentation is complicated, but we have complete algebraic control of this object. Now, time is running a little low, so in fact, I think I'm going to skip over some of this. So let me just say that that we calculated the Z. Yeah, please do.
Am I remembering right that do you also have a theorem like this for CP?
So I don't have a calculation in terms of generators and relations for CP. I do have some qualitative results of the CP equivariant cobordism ring, but maybe I won't say anything about that now. Perhaps if you ask at the end of the talk, I could say a little bit more about what I know does generalize, what I'm not sure generalizes, et cetera.
Sure. Cool.
Okay, great, thanks. So in any case, the next few slides just say essentially that the ROC2 graded coefficients of the spectrum can be calculated using similar methods. And so maybe let me just skip directly over this stuff, but the idea is that just as we had an explicit presentation of the Z-graded coefficients of omega C2 in terms of generators and relations, we have explicit calculations of the ROC2 graded coefficients of omega C2 in terms of generators and relations. Now, well behaved, the ROC2 graded coefficients are well behaved only whenever your multiple of alpha is a negative number. When the multiple of alpha, which is the sort of twisted dimension, it's the real sign representation, when that whenever you have a positive multiple of alpha, the algebra gets a little bit more complicated. In particular, the coefficients are no longer concentrated in even integer degrees. However, so on this slide, I've just listed sort of the good range, if you will, of the ROC2 graded coefficients, but I do have an understanding of the full ROC2 graded coefficients. It's just not as pretty of a picture as this sort of non-derived range. And this, so if you're familiar, for instance, with some calculations in equivariant stable homotopy theory, for instance, if you're familiar with the calculation of the ROC2 graded coefficients of an Eilenberg-MacLane spectrum like HZ, I encourage you to look at the diagram and notice how in the lower half plane, we have something that's essentially just a polynomial ring. And in the upper half plane, we have all sorts of bad things. Like if you include the upper half plane, you get some non-Noetherian, very complicated ring, and something similar happens here. And so it's sort of a general heuristic that including negative multiples of non-trivial representations yields nicer answers on homotopy groups. Whereas if you look at that upper half plane, you can get much nastier things. At least that is my understanding. All right. So we have just a few minutes left. And so what I want to do is try to answer question number 3, which is what is the relationship between the spectrum omega C2 and the stable cobordism spectrum MUC2? We know we have a map between them, and we'd like to understand that a little bit better. And it turns out that there's a very nice answer. The answer is that MUC2 is, in the ROG graded sense, a localization of the ring spectrum omega C2. To be more precise, what I'm claiming is that there's an element tau. There's an element tau in the ROC2 graded coefficients of omega, and that if I invert that element tau, by which I mean I form the so-called homotopy colimit of the following sequence. So I have omega C2, I can multiply by tau to get to this guy. I can multiply by tau again to get to this guy, etc. And it turns out that if I take the homotopy colimit, I get exactly the spectrum MUC2. And so it's this observation that will motivate the rest of the math we'll see over the next couple of minutes. So what I want to talk about is sort of how this localization observation, the fact that omega C2 localized at tau yields MUC2, how this relates to the theory of complex orientations. So let me remind you that a complex orientation of a C2 spectrum is just a ring spectrum map from MUC2 to EC2. This was the theorem of Cole, Greenlees, and Kriz, which says that complex orientations, while they can be defined as a certain cohomology class, are in fact classified by the spectrum MUC2. Now, motivated by this definition, I propose the following definition. A geometric orientation of some C2 spectrum EUC2 should just be a ring spectrum map, not from MUC2, but from the geometric cobordism spectrum omega C2. So that's my definition, and I'm sticking to it. The reason why it's a good definition is because it turns out there are many interesting examples of such objects. And I'd like to take a look at those over the next few minutes. So the important observation that sort of connects these two theories to one another, because I mean, you know, here's my geometric orientation definition, but people care about complex orientations. This is a well-known theory. People want to understand it better. And what's nice about this theory of geometric orientations is that it ties in very interestingly to the theory of complex orientations. To be more precise, the key observation is that if we have a geometric orientation of a spectrum EC2, then we can invert the element tau in EC2, again, by forming this homotopy colimit. And I claim that this spectrum is complex oriented. And the proof is very simple. It's just that if we have this map from omega C2 to EC2, then it induces a map on the localization at tau, where if we localize omega C2 at tau, we get the stable cobordism spectrum. And if we localize EC2, oh my goodness, what happened there? If we localize EC2 at tau, well, we get what we get, but it receives a ring spectrum map from MUC2, and so it has to be a complex-oriented C2 spectrum. Okay. So there are lots of interesting examples of these objects. The two examples I'd like to emphasize, aside from the spectrum omega C2 itself, are the following two examples. First of all, there's the Eilenberg-MacLane spectrum, not Eilenberg-MacLane spectrum. And this is the Eilenberg-MacLane spectrum associated to a constant Mackey functor on a commutative ring R. And so in this GROOT series, I think we've had, for instance, David talked about Mackey functors. I won't review Mackey functors here, but the idea is that Mackey functors are sort of the C2 equivariant analog of abelian groups. So in any case, it turns out that this spectrum is geometrically oriented. And another interesting example is the connective cover of equivariant complex K theory. And so this spectrum little kc2, I'm defining as the connective cover of big kc2. And so this is just a C2 spectrum with the property that its homotopy groups are the same as the homotopy groups of kc2, except I'm cutting off everything that is below dimension 0. So let me conclude with the following pair of theorems. Well, I guess the problem we'd like to answer for these examples is, well, we know that if we have a geometrically oriented spectrum, then if we invert tau, we obtain a complex oriented spectrum. And these are hard to come by. You can't just find complex oriented spectra all over the place. And so one interesting part of this theory is that if we have a geometrically oriented spectrum, we get a new complex oriented spectrum for free just by inverting this class tau. And so given a C2 spectrum, we'd like to identify this complex oriented spectrum associated to it. And we can do this by calculating the ROC2 graded coefficients of EC2, or at least it suffices to calculate the ROC2 graded coefficients of the geometrically oriented spectrum EC2. So I'll close with the following pair of theorems or propositions, which is that if R is a commutative ring, then the Eilenberg-MacLane spectrum associated to R is geometrically oriented. And if we stabilize it by inverting tau, we get the co-free spectrum on HR. And so as far as a proof goes, well, why is it geometrically oriented? Well, the point is that this map here, anytime we have an equivariant spectrum, it always maps to the co-free spectrum. And it turns out that this map is a connective cover in the equivariant sense. And so since omega C2 is connective, the universal property of the connective cover provides us with a lift, at least up to homotopy. And so this is our geometric orientation of the Eilenberg-MacLane spectrum HRC2. Now, if we want to calculate its stabilization, what we need to do is calculate the ROC2 graded coefficients of this Eilenberg-MacLane spectrum. Now, again, here I've only drawn the good range. So this is the lower half plane. And in fact, I've even omitted some stuff that might be on the odd multiple horizontal lines. But in any case, the point is that whenever we, yeah, go ahead.
I think I missed, so R is just a commutative ring. There's no action, right? Like I'm just wondering, how do we turn it into an equivariant spectrum?
Associated to any commutative ring is a constant Mackey functor, or essentially
just take the constant Mackey functor.
Precisely, yeah. So it is like that ring R is a G module in the trivial way. C2 just acts trivially.
Right.
Okay, great. And the point is that multiplication by tau just takes us down these diagonal lines. And so if we take the co-limit along multiplication by tau, we just end up with R adjoins some generator U modulo 2U. And this is exactly the coefficients. This is exactly pi star of this co-free spectrum. And so this is at least a sketch of the proof that whenever we stabilize the Eilenberg-MacLane spectrum, the resulting complex-oriented spectrum is this co-free spectrum, which represents Borel cohomology. Let's take a look at a more interesting example. So here we have big KC2. Again, this is C2 equivariant complex K theory, and its homotopy groups are given by the following thing. So in each even degree, we have the representation ring of C2, and then this element V is the Bott element, which gives us this 2 periodicity in the homotopy groups of KC2. The connective cover is just this spectrum, which is characterized by the fact that its homotopy groups are the same as the homotopy groups of KC2, but we cut off everything that occurs below dimension 0. Now, on the other hand, there's a whole sort of sect of the literature which is dedicated to this other version of connective equivariant K theory. So this was constructed by Greenlees, and it's a C2 spectrum, which is KUC2. It's not the connected cover of K theory. However, it does satisfy the sort of desired formal properties. It's non-equivariantly connective K theory. It's complex oriented, and its coefficient ring turns out to classify multiplicative C2 equivariant formal group laws. Now, I haven't said anything about what those are, but these are sort of the formal properties that you'd want of an equivariant connective K theory spectrum. And so I guess the final punchline of my talk will be that if we start with the honest to goodness connective cover of K theory, then that is a geometrically oriented spectrum. And if we invert the class tau, we actually obtain Greenlees connective K theory spectrum. So this theory of geometrically oriented spectra provides a new and interesting link between honest connective K theory and then this sort of ad hoc, well, maybe I shouldn't call it ad hoc, but this sort of important equivariant analog of K theory, which is not actually the connective cover. And so just to show a glimpse of how this is proved, here we have the good range of the coefficients of connective K theory. And you can just explicitly calculate that if we multiply by tau, by which I mean we take the colimit along these diagonal maps, which are multiplication by tau, then this induces an isomorphism on homotopy groups. So if we take the ROG graded homotopy groups of KC2, we mod out by tau minus 1, we get exactly the homotopy groups of Greenlees connective K theory spectrum. All right, so I've run a little bit over, but let me just advertise that there are plenty of further directions to study. I mean, for instance, can we always represent cobordism by a G spectrum? Can we calculate more general coefficient rings for larger groups? Can we extend this theory of geometric orientations to larger groups? And maybe most importantly, and something which I've studied a good bit and have some answers, to is the question of what is the connection between geometric orientations and omega C2, and then on the other hand, equivariant formal group laws, which are these complicated algebraic objects. That's the end of my talk. Thank you all very much for coming and participating and asking questions. I hope you all have a good day. And if you have any more questions, please do let me know.
Great. On behalf of everyone, I'd like to thank Jack. Are there any questions to be included in the recording?
Hi, thanks for the talk. So I don't 100% remember all this, but if you take MO,
okay.
then there is sort of then often equivariant Bordism is the same as MO, right?
So in the non-equivariant setting, it's true that like omega star unoriented is equal to MO star. This is true.
Right, but isn't something also true equivariantly?
Yes, it is. And so the idea, and perhaps if you're familiar with the literature on this, the notation with which you might be familiar is that omega C2 unoriented is isomorphic to little mo C2 star.
Right.
And what I have called omega C2 in my talk is sometimes called little mu C2.
Right. Yeah.
So if you look at, well, maybe let me not guess the references, but yeah, it is not the case that I conjured the spectrum.
Right, and then the
natural
capital MUC2 was
for-
where you invert this this Tom element, I think it's called.
Yeah, that you're exactly right. And so more generally, if you take this spectrum MU or MO or whatever, and then you invert a family of these tals, it turns out you have more of them if your group is not just the cyclic group of order 2, then this does in fact recover the stable cobordism spectrum. And similarly in the unoriented case.
Basically what I was wondering if you had so I didn't know this, that so I learned the unoriented, the real version.
Right.
So I sort of never really thought about the complex version. Is there sort of a good answer for why, for the real version, you do have that little MO star is boardism, but that you don't have this for MU?
Here's an answer, and it'll be up to you to decide whether or not you like it. What I know is that, for instance, one place where this equivalence is proved is in Stefan Schwedes, if I'm saying that name correctly, in his notes on global homotopy theory. Yeah, and the proof that this unoriented spectrum, little mo, represents cobordism of G manifolds consists of either 40 or 50 or 100 pages or something like that. And so I just have not had it in me to try to like go through and check like, all right, if we are in the complex world, does this also go through? Does this also go through, et cetera? So this is something that I desire. I mean, I would like to know that this holds in general, and my prediction is that it does.
Okay.
In the current work, since I was focused on calculations, I just used this sort of slick proof using long exact sequences to guarantee the representability.
Okay, so so you weren't trying to suggest that this wasn't true.
Yeah, I believe that it is true. It's just a careful proof has not appeared in the literature, and so I don't want to claim that it's true before I know that it really is.
I see. Okay, cool. Okay.
Yeah, great. Thanks for your question.
Yeah.
Thanks for the talk too. I wanted to ask about complex orientations. So classically, when you have a complex-oriented cohomology theory, you can compute also the cohomology of classifying spaces, BUN, just by knowing that you have the thing for CP infinity. And I was wondering if you had something similar here, like if you're G complex-oriented, can you compute the cohomology of BUNG?
Yeah, the shortest answer is yes. Let me say some stuff about it. So if E is complex oriented, then maybe the first case that we want to understand is BU of 1, right? CP infinity. And in that case, I mean, sort of the right analog of CP infinity would be the space of one-dimensional subspaces of, now again, here, maybe let me restrict to the case of C2, though something holds more generally. Lines in C infinity plus C infinity alpha. So this is a complete universe. And the idea is that this thing is not a power series ring. However, it is a product on all of these. So you have 1 sitting inside of this ring. You have the complex orientation X. You have X squared. You have X cubed. But you also have things like X to the 3 plus alpha and X to the 3 plus 2 alpha, et cetera. And so what's true is that basically for any choice of a sequence of X's and X alphas, you obtain an isomorphism between this cohomology group and this sort of free product on the X alpha, or the XVs, if you will. And so this is sort of related to the fact that if you're in C infinity, there's essentially a unique walk through finite subspaces of C infinity. You've got C0, C1, C2, et cetera. But if you're in a complete G universe, you can step in the 1 direction, or you can step in the alpha direction, or you can step, if you have a big group, in the beta or gamma direction. And corresponding to any such walk through this infinite dimensional vector space or representation, you have a different product decomposition of this cohomology ring. So if this answer is to inspire anything, it should tell you that things are definitely more complicated in this situation.
Is it naive to call this like a, I don't know, a C2 formal power series ring? And one variable?
I think it's suggestive. I mean, I maybe I won't do it now because I don't have the details to fill in, but that's right. I mean, maybe I should mention that there's work of my advisor, Igor Kriz, and people like Abrams and Cole and Greenlees. And they've written several papers about these objects. But yeah, there's, I don't know, there's a beautiful story that's hidden in all of this, of which I've only seen the tip of the iceberg. So, you know, there's a lot more to be discovered. So yeah, that's a great question. Like, is there a notion of like a genuine power series ring where this weird thing where each flag gives you a different sort of product basis? Yeah, that might be a very naturally defined or naturally occurring object. But I think there's no known answer, at least not known to me.
But I think the difference would be that there's many. Like there's not just one.
Yeah, that's right. I mean, the right notion, according to whoever I am, right, is that it should be some structure where for any choice of flag, you have this decomposition, but it would be nice if you had some description that was just self-contained and said like, it's this ring modulo, or with these generators modulo these relations, and theorem is that you have these sort of decompositions in terms of the various sequences. But to my knowledge, no such thing exists. It's all very complicated. Like this equivariant algebra is hard. I don't know, maybe to some of you it is easier, and I would like to hear that, but yeah, things are pretty complicated.
Can I also ask if I understand correctly? So you said that if you take the connective cover of big KUC2, then this is going to be geometrically complex oriented or geometrically oriented. So you're saying that it's not complex oriented.
Exactly. This is an example of a spectrum. And in fact, both, sorry, let me return to an appropriate slide. Here we go. Yeah, both of these guys right here are geometrically oriented and not complex oriented. So that also makes them interesting because these are like very naturally occurring spectra, which are complex in some sense, but they're not complex oriented. So this offers some resolution to that sort of, I don't know, narrative tension.
Okay.
Could I ask something about the group law story?
Yeah, go ahead.
Yeah, so somehow you said you thought a little bit about these equivariant group laws, and I was wondering whether there's like a concise description of what a G equivariant formal group law is, or something in that direction.
Yeah, there definitely is. So I'll refer you to the paper with the appropriate title, which is Equivariant Formal Group Laws by Cole, Greenlees, and Kriz. But I can give a brief description. So the idea is that in the non-equivariant world, formal group laws, they look like this, right? They're power series rings in a variable X. And so this thing is like the ring of functions on the formal neighborhood of a point. So algebra geometrically, like spec of this thing is a point, but you have sort of all of this tangent information or something like this. And if you couldn't notice, I'm stepping out of my realm of comfort now, so take it with a grain of salt. But in any case, the idea is that in the G equivariant setting, we have some ring R, which is not actually a power series ring. In the examples we care about, it's the cohomology ring of this space of lines in a complete universe. But the idea is that it is axiomatized so as to reflect that this is the ring of functions on a formal neighborhood of the Pontryagin dual of the group G. And so this is a group which is, at least if G is finite, it's isomorphic to G itself. So for instance, like if G is equal to C2, then G dual is just equal to, it's equal to C2 again, but we might call the elements like 1 and alpha instead of 1 and X or whatever the other generator was. And so it is in this world of formal algebraic geometry that G equivariant formal group laws exist, and they exist as sort of, like for instance, if you have an algebraic group G in which a finite group G is embedded, G prime is embedded, then if you complete at that subgroup G prime, you obtain an object like this. So there's
You
some
also
stuff.
mentioned work of Stefan Schweder before and like global homotopy theory. Do you expect there to be a similar story with formal group laws, maybe with extra equivariance data and restriction and transfer morphisms, maybe?
Yeah, that's exactly right. So let me, in fact, advertise this theorem of Haussmann, which is a beautiful theorem, especially in light of the fact that, sorry if this is nauseating, flipping through these slides, especially in light of the fact that this conjecture was open for 20 or 30 years or something. Well, let's say 20 years. This theorem of Haussmann, which says that the coefficient ring of MUG classifies G equivariant formal group laws. This is proved using global homotopy theory. And in fact, in his proof, he gives a totally different characterization of what a G equivariant formal group law is. Or in fact, what he really defines is global formal group laws. So I encourage you to check out his paper, which is called, I think, Boardism rings and global group laws or something like this. It's a very nice paper.
Fantastic. Thank you so much. Thanks.
Thank you.
And just for completeness, the what you gave before is only for for abelian groups, G.
Yeah, that's right. And in fact, G equivariant formal group laws are defined only for abelian groups, at least at the moment. Maybe I don't have a great answer to this, but yeah, if you look at this Haussmann paper or the Cole-Greenlees-Kriz paper, these notions are defined only for abelian groups G. It's open what the right notion is for non-abelian compact Lie groups.
Could I ask a quick question? So you have a description of this geometric Boardism ring for C2 complex manifolds.
That's right.
So elements in this ring should be represented by equivalence classes of actual stably almost complex manifolds with C2 actions, right?
That's right.
So for which ones do we know what the generators are?
Yeah, this is a great question. It is basically it is the last step that I need to complete before I can submit my paper for publication, is how to identify these generators in terms of representing manifolds. I do have some answers, however, like for instance, this generator Q1 is given by the zero-dimensional manifold C2. So this is just the free C2 orbit.
Okay.
And for instance, another interesting example is that that if I look at minus Q2, this is the class of the projective space CP of 1 plus alpha. So this is the space. Right. And so, yeah, then the question is, what is the pattern, right? And well, I don't know. The pattern seems complicated, but basically what one can do some, yeah, if you want a more precise description, the idea is that you can map from this geometric cobordism ring, which is very complicated, to the geometric fixed points, which are much more understandable. And furthermore, you can pass via the Hurevich homomorphism to something even more sort of understandable. And so the hope is that these elements can be described in terms of some sort of formal group law theoretic data. And this is akin to the question of, if you look at the Lazard ring, how do you represent generators of the Lazard ring by stably almost complex manifolds, which is a non-trivial question in general. So that's and maybe not exactly an answer to your question, but it's some comments on your question.
This is very helpful. Thank you.
All right. Thank you.
Yeah, and great talk, by the way.
Appreciate it.
Yes, thanks again for speaking, Jack. I'll go ahead and stop the recording here.